All right, so this is going to be the second day for related rates. We're picking up right where we left off yesterday. So you should have done page 209, numbers 1 through 4, and then quick check number 1 and 2 from the end of the lesson. And so right now we're going to pick up right here would be level 2 and level 3 problems. And one of the most important things is to be able to visualize what's happening, identify your variables, and then set up your equations that will relate. Many of the equations that are going to relate are not from calculus. They tend to come from the earlier classes. So that's really important that you remember all of the stuff that you had in your 4 previous courses. Okay, so a baseball diamond is a square whose sides are 90 feet long. Suppose a player is running from second base to third base. Here's your runner. There's your runner. From second base to third base, and has a speed of 30 feet per second. So I'm going to write that down. Okay. At the instant when he is 20 feet from third base, at what rate is the player's distance from home plate changing at that instant? So you can see here in the picture, they've kind of done a nice job of giving you a diagram. And I've outlined there, so you have a triangle. And keep in mind that that's really a right triangle. And so what we're really looking at is he has a speed. I'm going to draw a right triangle here so I can show you. So here's your triangle. And clearly not drawn to scale, but this is 90. Okay, so I'm rotating my triangle so that I can see he's 90 feet from home plate, so this would be home. And the runner is here, and he's running towards third base. And he's exactly, according to the wording, 20 feet. So we're looking at, there we go. So this is his distance. So when he was here, he's this far from home. When he's here, I've gone in my picture, he's this far. So you can see, as he's actually getting closer to third base, he's actually getting closer to home, okay? So the distance that we're talking about is actually this distance, which would be his hypotenuse. So, hint, 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 we have a right triangle. We know one leg. We know the second leg. We can find the exact distance at 20 feet by using what? Yeah. Where D is my distance from home. Now, one of the things that you need to note is you should be writing what everything is on your picture, especially if you're going to need help. It's visually helpful if we can see what you're doing, okay? So here I have I have a relationship between the distance that I am at that instant. So this is at a specific moment. I can figure out exactly how far I am. Now, in general terms, I'm using Pythagorean theorem, where this is my distance. B, I'm going to call this B, and I'm going to call this A. Now, is A changing at all? A is not changing at all. So what's the derivative of a constant? The derivative of a constant is 0. So when I take the derivative of this, I want to write that down so that I remember that dA dt, the rate at which A is changing with respect to time, is 0. It's a constant. It is not changing. Now, I'm not taking the derivative yet. I'm just writing down all the knowledge that I know. The second thing that I know, given in the words in the problem, and this is really important, I was told that dB dt is equal to 30 feet per second. Now, this is important because it's not given in the word here, but what it says is he's running from second to third. Now, if B is defined as my distance to third base, then that distance is decreasing, which means I need to put a minus sign in front of the dB dt. Okay? The distance from third base B is decreasing, I need the minus sign. Okay? So at this point now, I think I'm ready to take my derivative. So let's go ahead and do that. So the derivative of A would be 2A, I'm writing everything out, dA dt, plus 2B dB, my bad. There we go. 2B dB dt, and then 2D, the change in the distance per time. Now, you could have used any other letter here. So this right here, remember, is the distance to home. So I use the letter D. Please feel free to change it because 2D, dd, dt seems confusing, but that's fine. Okay, now remember what I said up here. So this whole piece is going to be 0. Now the distance given, write it. dB dt. Remember, this is in feet, and this is feet per second. Now, how far am I at that instant? So, doing some math here, 8100 plus 400 is equal to 8500. 0081. So, okay. So the square root of 8500 is D. So I'm just going to leave that actually. I'll use my calculator at the end if I have to. I probably won't today. And so now I have 40 times that, which is negative 1200, all over 2 root 8500, which is going to be dd dt. Now, I tend not to use a calculator, but, I mean, I can simplify this without that. And so I would leave my answer. And what this says, here's the important part. What this says is that the distance to home is decreasing at a rate of 1200 divided by 2 root 8500 feet per second. Okay, this is, where's my units? So this right here, feet per second, correct? And then over here, dt is the rate at which it's changing in feet per second. So the distance is changing in feet per unit of time, which was given as seconds. So the negative tells me it's decreasing. The boxed number here tells me the rate. Okay, that minus sign tells me it is decreasing. And if you look at the picture, it should all say the same thing. Look, these hypotenuse, I don't know if that's how you say it, hypotenuses? Who cares? Those are decreasing, okay? So answering the question, at what rate is the player's distance from home plate changing at that instant? It's changing at 1200 divided by 2 root 8500 feet per second at that instant. Okay? So keep in mind, I used the Pythagorean theorem twice. Once with numbers to come up with one of my values, and then I evaluate the derivative with just variables, plugging in all the information given for the specific moment that we're talking about. Okay, in figure 3.4.5, so again, the picture is given. They're much, much harder when you have to derive the picture yourself. And so here we go. It says, in figure 3.4.5, we have shown a camera mounted at a point 3,000 feet, from the base of a rocket launching pad. If the rocket is rising vertically, so now we're only changing in the vertical. The camera is not moving and the launching pad is not moving. So what is changing is, according to this picture, H is increasing. And they're telling us that dH dt is equal to 880 feet per second when it is 4,000 feet 4,000 feet above the launching pad. How fast must the camera elevation angle change at that instant to keep the camera aimed at the rocket? Okay, so let's just do this for a second. I'm just going to show you something. Here's the camera, and here's our rocket. That's a rocket, by the way. And so our rocket is going to go up. So right here, the camera has that angle. Now, as the rocket is launched into the air, it's going very fast, into the air, the camera is still here, but now look at this angle of elevation. So the angle of elevation should be increasing, which means at the end, oh dear, my computer's going to freeze. Don't panic. If it freezes, I will have to restart. Oh no. Okay, I'm going to keep going. Sorry. Okay, so I'm looking for d theta dt. I want to know the rate at which the angle is increasing with respect to time. And the reason I said it's increasing is because in my head I have to visualize this should be a positive number when I'm done. It is increasing. It is growing in size. Okay? So let's come up with a relationship that can relate the given information to the angle. So I need a theta equation. And so we say, hello, pre-calculus, welcome to calculus. So I have this leg constant, and I have the opposite leg not constant. And so which trigonometric identity will relate this angle with this side and this side? And I'm hoping you're all saying tangent theta equals the height over 3,000 feet. Okay, which means, I'm going to write it this way, the tangent of theta is equal to 1 over 3,000 times h. Now, I could use opposite over adjacent, and then I would use quotient rule, and then recognizing that the adjacent leg is not changing, so that derivative would be 0. And that's just more work. I don't need to do that because I know it's constant, so I'm just going to pull out the constant. Okay, I'm just pulling out the constant. Okay, so now here's my equation that's going to relate my two sides. Okay, now the good news is, if I look down here, oh, here we go. Sorry if this crashes. So if we look down here, they've given us the sides. Look at that. So they've given us some information here. And so what I want to do is I want to say, okay, well, let's take the derivative of this thing and see what I get. So the derivative of tangent is secant squared theta. Chain rule, d theta dt, is equal to 1 over the constant stays. Derivative of this is dh dt. Now, I'm going to say this because I think it's important to say right now, this is not the only way to do this. This is my method. The other option is to solve for tangent, to solve for theta right here. Once I see tangent theta, I can solve for theta, get the inverse tangent, and then I can use the derivative rules from section 3.3. That is an option, and if you are happy to use inverse functions, please, please go for it. I prefer to do it this way because I'm much more comfortable with the chain rule. But this is not, I repeat, not the only way to do it. Okay? So in my brain, this is my method. And so the reason that I'm using this, they gave me all my lengths. So now I can plug everything in that I know, because I know this. They told me this was 880 feet per second. I know 1 over 3,000, that's a constant. I do not know d theta dt, so I'm leaving that. That right there, kiddos, is what I'm looking for, okay? I'm looking for d theta dt. And now secant squared. So now I have to go back to my pre-calc, and I have to say, okay, well, what is secant? Secant's 1 over cosine. So now I'm coming to my picture, and over here, and I look at the cosine of theta. Remember, this is my theta. And so I say the cosine is the adjacent over the hypotenuse. And I'm cheating a little bit because the 3 zeros are going to cancel away, right? So it's really just the adjacent over the hypotenuse, so 3/5. But secant is going to be 5/3. So I'm going to come over here, and I'm going to say 5/3, and I'm going to square it, because I have 2 secant thetas, okay? So now this to me is super easy, because I'm just going to flip and multiply. So I'm going to get rid of some zeros here. And so over here I have 88 over 300, and I could simplify at this point, but I'm going to leave it for right now. And then I have d theta dt, and I'm going to take this, which was 25/9, and I'm going to multiply by 9/25. So I'm going to multiply both sides by 9/25. And notice I am not using a calculator. At this point, if you feel free, you can just plug in those numbers and isolate and solve, and that's totally fine. It does not matter to me. I'm sure Mr. Clinton does not matter to him either. So I'm going to divide both sides by 3. For whatever reason, I like doing it without a calculator. Ricardo, I don't know. So d theta dt, and for 25, for 22. And so now I get 66 over, what is that, 625? And remember, theta is in radians. It does not have units, but it's radians, so it's radians per second. Now, again, if you like your calculator, go to town and start pushing those buttons. Okay? Now, one of the things that's important to note is we do trig in here in calculus. Trig is only done in radians, which is why I say radians per second, or 66 over 625 radians per second. And the reason is, notice this is a positive value. That's good. But in Calc, trig is only done in radians. So if your book gives you the answer in degrees, remember there's pi radians per 180 degrees. Okay? So in your thinking bubble, that's your conversion factor. So if you want to check and your book uses degrees, there you go. It was not specified, so I'm going to go ahead and leave it as positive 66 over 625 radians per second as my d theta dt. Okay? So option 1, you could have done it. Option 2, using inverse tangent. It would work just the same. All right, and the third example, FYI, on the AP exam the last few years, related rates problems have been conical. One was a coffee pot funnel. They also use rate of change in terms of heat loss. So, and they give you an equation. So definitely an important concept. So let's take a look here and see what we can do. Suppose that liquid is to be cleared of sediment by allowing it to drain through a conical filter. Again, the picture is given, so it makes it super easy. A conical filter that is 16 centimeters high, that's the total height, and has a radius of 4 centimeters at the top. Again, that's the total cone. We're looking at just the part that's being filtered, okay? So suppose also that the liquid is forced out of the cone at 2 cubic centimeters per minute. Okay, so I'm going to pause right here, and here's what's important. 2 cubic centimeters per minute. What's measured in cubic centimeters? Volume is measured as a cubic function. So this that they're giving me is a dV dt. I'm forcing out a certain quantity of water, a volume of water, at a constant rate of 2 cubic centimeters per minute, which means out of the cone is a positive rate, so the amount in the cone is a negative rate. Do you think that the depth of the liquid will decrease at a constant rate? Give a verbal argument that justifies your conclusion. Okay, so in this case, you're giving a verbal written description. In this case, I can't hear you talking, but I want you to be thinking about, do you think that the depth of the liquid will decrease at a constant rate? And then say why. Okay, so think about that. Pause. and write down your answer. You should be pausing. You should be pausing. Write something down. Whether you're right or wrong is irrelevant right now. Give a verbal argument that justifies your conclusion. Part 2, B, find a formula that expresses the rate at which the depth of the liquid is changing in terms, excuse me, of the depth. So depth, according to this picture, is given as y. And so I want to know how the y is changing. Okay? And now look, this diagram is telling you something. The same volume has drained, but the change in height is greater near the bottom than near the top. So they tell you, that's funny. If you looked at the picture, I didn't look at the picture till just now. If you looked at the picture, you would know that the height is definitely not going to decrease at a constant rate. And the reason is, this distance here is much, quote unquote, thinner. I'm using the word thinner just because it's narrower than here. So the diameter of the cone, if you will, is decreasing, which means that the y must also be changing at a different rate, because look here versus looking here. Okay, so just looking at the pictures, we can get the answer to part A. The answer is no, it will not decrease at a constant rate, and the reason is the cone is narrower at the bottom than it is at the top. Okay, so think about pouring water into a cone. Okay, it's the same idea. So find a formula that expresses the rate I'm just putting a little note here to you so that you can see that they're giving you the answer here. Okay, so find a formula that expresses the rate at which the depth of the liquid is changing in terms of the depth, and use the formula to determine whether the conclusion in part A is correct. Okay, so now I have to come up with an equation that relates the depth of the liquid, in this case y, which I'm going to call height actually, the height of the liquid, because I need to think about a cone now. And so what are the equations for cones? Now, at this point I'm walking over, I'm grabbing the book. You should also be grabbing the book. In your book, inside the front cover, on the very front cover, it says geometry formulas, and you'll see this formula. I'm writing it down. The volume of a cone is 1/3 pi r squared h. Now the second formula that's right there in the book, S equals pi r L, that has to do with the surface area or the amount of material needed to make the cone. So right now, and notice I mentioned earlier that this is dV/dt, so this is going to be the formula that we use. Now I said I was going to use H. Your book in the diagram given is using Y. Okay, so one of the things to note, and I'm going to give you a little hint, they gave me the radius here, and they gave me the y here. And so in my head, I need a relationship between y and r, or h and r, because I'm going to have these two variables in here, and so I'm going to have to relate those. So one of the things I want to do is notice that the radius is not constant, and neither is the height. However, the cone ratios are constant, which means that the radius to height ratio is going to be a constant 4:16. So I'm going to go ahead and I'm going to solve this, because see, I'm looking for dy dt, so I'm going to go ahead and solve this for r in terms of h. So r is equal to 4/16 h. So I'm now going to go ahead, and that's true anywhere in the cone, this relationship is going to be true. So I'm going to come over here to this equation, and I'm going to plug in 4/16 h quantity squared times h. And then, let me make sure you realize, I'm using h, the book used y, so I'm going with h. And so if I do some algebra, I'm going to get ooh, this is a big number, 16 over Mr. Clinton's favorite number, 256. I can reduce that to 1/4 in here. So I get 1 over 16, h squared times h. So I'm still just doing algebra right now. So I'm going to get pi over 48 h cubed. And now pi over 48 is a constant. So what I want to do is I want to take the derivative of the left and the derivative of the right. The derivative of the left is going to be dv dt, which remember, earlier they told me was a constant 2 cubic centimeters per second, per minute. Let me reread. Per minute, Ms. Collins, per minute. Don't screw up your units. And then I want to derivatize the other side. So that's a constant. I'm going to pull it out front. 3h squared dh dt. So a little bit more algebra. Pi over 16 is equal to 2. And now they told me, they told me up here that the rate at which the depth of the liquid is changing at the instant when the liquid is exactly 8 centimeters deep. So now they're telling me that h is equal to 8 centimeters. Someone's knocking on the door. They're going to have to wait. So now I'm going to take 8 and I'm going to square it because that was given in the problem. And so now I want to simplify. So 64 divided by 16 is 4 pi. So this is going to lead me to the rate at which the height is changing is 1 over 2 pi. And that's going to be centimeters per minute. And I'm going to leave my answer in terms of pi, because that's just a pretty number, okay? So important things from this problem. 2 steps, super important. The first thing we had to do was we had to relate radius to height, because that becomes super important, radius to height, so that I can make a substitution. In this equation, I have 2 unknowns. I have to have a second equation to make that substitution. Okay? Again, I could, but I don't want to. I do not want to plug into the original equation the known values. I only plug in the known values at the very end. Okay? I need to take the derivative of everything at the very end is where I'm going to plug in my constants. Okay? So here's what you're going to do now. You're now going to finish quick check numbers 3 and 4 on your own tonight. 3 and 4 on your own. You can check page 211 for the answers. It's only the answers that are going to be there. Please draw a picture, label your diagram, write your equations, and then show your derivatives. Okay? Draw a picture, label your diagram, and then show your equations. Okay? Those are the 3 steps that are most important, especially if you're struggling and you need additional help. Okay? So all you're going to do tonight now is check numbers 3 and 4 for quick check. You're going to do them, check them, and then tomorrow when you come in, we'll have a worksheet for you. All right? Good luck.